I had to acknowledge you. Okay, so yeah, so this is the outlook of my talk. I'll be giving a short introduction to interferometry, phase interferometry, and then what's the difference with intensity interferometry, which is the one we are using in Cherenkov telescopes. Then how we do it in Cherenkov telescopes, and then the kind of science that we are already doing with interferometry in Cherenkov telescopes, specifically with MAGIC and the CTA LSTs. So this is really very much a primer. I hope nobody feels insulted when I introduce interferometry. But I think it's a nice introduction because intensity interferometry is not so well known. So I start by comparing with phase interferometry or amplitude interferometry. So I think you all remember this old experiment by Young, the double slit experiment, where you have a plane wavefront arriving at a wall with two slits, and this makes the light produce an interference pattern in the next wall, right? So with interference pattern means that you will have maxima and minima, okay, following this sinusoidal shape, okay. The maximum will be at the point where you see the same, where is the same distance from the two slits, right? So in real life, stars are not point sources, okay. So it's not a plane. So you cannot hear me very well. Well, no. Keep talking. I'll try to keep the microphone in place. So yeah, so in real life, stars are not at infinity, so it's not a plane wavefront. You have a distribution of angles, right? Stars are very small, but there's a very small angular distribution. And we are in fact interested to measure this distribution. We can measuring the distributions means that you measure the angular size of the star, okay? So what you have here is if the point sources as infinity is as before, is a plane wave, but with an angle, you start to move this distribution of maxima and minima. The maximum is shifting simply because the point where it's the same distance from the two slits is different, right? So this distribution of maxima and minima is shifting, and when you put everything together, what you have is a reduced visibility in this distribution. When the baselines, so the distance between the two telescopes, the two slits, which effectively in astronomy are two telescopes. When the distance is very small, so the baseline is very small, you still have this strong maxima and minima in the interference pattern. But when you start to separate the telescopes, or you go for longer baselines, this pattern, as you see, is getting the amplitude is decreasing, right? So you don't see the pattern so well. When you are far away, you don't see any pattern, okay? So this is what you typically do in phase interferometry. You have your two telescopes when they are close to each other. You see what is called visibility, that is the difference between maximum and minimum divided by maximum plus minimum. The visibility is very big here. You see very nicely the pattern here, and it starts to go away. Okay, when you are far away, you don't see any pattern anymore. And by measuring how this visibility decreases with baseline, this is what is shown here, visibility as a function of baseline. There's a characteristic pattern in this evolution with baseline, and the shape of this pattern, so the width of this pattern in baselines gives you an idea of the diameter of the star. So for a small star, here is 1.5 milliarcseconds, for instance. This is a lambda of 400 nanometers. The visibility drops at around 50, 70 meters is gone. This is the first minimum. Instead, for 0.5 milliarsecond, the even smaller one, the visibility stays on and goes on and on until 200 meters and so on. So from this, it should be clear that you are able to measure this dependence of visibility with baseline. You are able to measure the angular diameter of a star. Okay, so that's basically the key of how you do phase interferometry. Okay, so this was put to work actually already in 1921 by Michelson and Pease, actually in Mount Wilson in California, December 1920, where they actually used the existing, the 2.5 meter optical telescope, but they put an arrangement here with several mirrors, and they made the mirrors interfere with a baseline from 0 to 5.5 meters. They played exactly this trick, okay? And they could measure for the first time the diameter of Betelgeuse, which is huge, is 47 milliarcseconds, okay? This is how they did it with these small baselines, okay? So now Betelgeuse is the largest diameter star in the sky. Most of the stars are weaker and smaller, okay? So with a baseline of less than 5 meters, it was impossible to measure any other star, simply. So, and the point here is that it's very difficult to increase the baseline. Why? Because the wave oscillates very fast, so you cannot digitize the wave. A light wave oscillates in less than 1 picosecond. You have a period here. You see 1 femtosecond for visible wavelengths or so. So that's the typical period. You cannot digitize that, right? 1 femtosecond digitization is impossible. And if you want to bring the light, like they did here, they brought the light together to a detector to create interference pattern. It gets very difficult because the optical path gets distorted by the atmosphere, and then it gets distorted in the ground, okay? So it's very difficult simply to reach these precisions in the optical path of better than 50 nanometers, huge precisions, right? So it's very difficult to do this kind of interferometry with longer baselines. This is not the same in radio. In radio, the wave oscillates very slowly. You only need, for instance, at a frequency of 175 megahertz, you only need a precision in the optical path of 10 centimeters, meaning that already in the 70s, you were able to do interferometry. It can actually, this oscillates, the wave oscillates so slowly that you can even digitize the wave and save it to tape and do whatever processing offline, okay? So radio interferometry developed very, very quickly. In the 70s, you had the VLA already built. They started to play in the 1990s with BLBA, very long, much longer baselines, talking about baselines up to 8,600 kilometers and reaching angular resolutions of 40 milliarcseconds. Okay, so the data are stored and processed offline, as I said. So, well, you know very well, the latest development is actually this Event Horizon Telescope with huge baselines, planet long baselines, pre-existing telescopes, but made to work together, working at these frequencies up to 450 gigahertz, and reaching this amazing angular resolution of 50 microarcseconds, okay? And you know all these amazing discoveries with EHT, okay, the surroundings of black holes and so on. So invisible things are evolving and have evolved in the last tens of years, and the state of the art is essentially this Chara array, 6 1-meter telescopes in California, where you can reach 200 microarcseconds resolutions with baselines of some 100 up to 300 meters, okay? And gravity is a state-of-the-art detector in the VLT, is doing interferometry in the VLTI, achieving resolutions in the infrared of 2 milliarcseconds or so, okay? It can also do astronomy with 50 microarcseconds precisions. Okay, so visible is going on, but it's mainly restricted to the infrared. and the baselines that are reached are up to here hundreds of meters with Chara and small telescopes. So is very much restricted, as I said. Okay, so what I'm talking here is about intensity interferometry, not phase interferometry. Okay, we can do something alternative by considering that light is not as simple as a sinusoidal wave. In reality, photons come from many points in the sky, in the star, random positions with random phases and random wavelengths. There's a distribution of wavelengths. There's no one single wavelength. Okay. This was already known back in the 1950s, right? And it's very simple to understand, I think, with the concept of beats. So if you take two waves or two different frequencies, nu1 and nu2 here, these two waves are slightly different frequencies. And when you bring them together, what you get is a pattern like this, okay? Here is rather white. It gets less white and then white again. So this is what in music is actually called beats. So you got this fast oscillation, but then you got also these slower oscillations. Okay, and you consider many sinusoidal components. So not only nu1 and nu2, but several nu1, nu2, nu3, and so on randomly. Okay, with random amplitudes, you get a pattern that looks like this in time. Okay, so you get these kind of oscillations. Sometimes they are small, sometimes they are large, and they happen at all scales. So even at longer time scales, you also get these kind of oscillations that come from the interference of different waves, different wavelengths. Okay, so there's always some kind of modulation for any time scale. This is what I show here. So if you look at femtosecond scales, very short scales. Imagine you look at the light of a sky with femtosecond time scales. Then you get huge changes in the intensity of the light of the star, simply due to this effect, simply due to this interference. If you go to picosecond scales, you still see oscillations, okay, but they are smaller, okay. And you go to nanosecond scales, you still see these kind of patterns, but they are still less wide than before, okay. So it still changes, but they are smaller. But there's always a modulation, even if in nanosecond scales, for instance. So what we do in intensity interferometry is we look at this kind of modulation in 1 nanosecond, typically, time beams, okay, in 2 different telescopes. And if the telescopes are relatively close to each other, you see these kind of modulations at the same time in both of them. You digitize, because now you're working with nanoseconds, so you can digitize. You digitize, and you look at the correlation in time of the 2 signals. Okay. And in principle, because you digitize locally, it's like radio interferometry. You can go to indefinitely large baselines. So you could go to 100 kilometers. You could go to whatever. Okay, because you make the correlation offline. Okay. That's essentially how it works. So when you have a short baseline, as I said, these oscillations are common in time at the 2 telescopes. So you see a strong correlation. As you go farther and farther away, you start to lose the correlation. And here, essentially, the pattern is changing completely independently at the 2 positions. Okay, no time correlation. When you look at the time correlation or the visibility, this is the one I showed before. So the dependence on time of the in-phase interferometry, and this is what you see in intensity interferometry when you see when you look is the visibility square actually. Okay, instead of visibility, in phase interferometry, we can see the visibility square. Okay, and this is proportional to the correlation that we measured. Okay, and they have similar spatial scales. Okay, we are also talking about these 100 meters that I mentioned before. So you put the telescopes typically at these distances. You also see a pattern of correlation that falls down and is also proportional or depends inversely actually with the angular diameter of the star. Okay, so both interferometers have the same angular resolution. We can measure exactly the same kind of stars with the two type of interferometers. This was actually done back in the 1970s in Australia by these fellows here. However, the instrument was not very sensitive because the telescopes were not very big, because there were also the electronics was slow. Okay. So this technique essentially went to sleep for many decades. Okay. Now it's time for a revival because we have these Cherenkov telescopes, and Cherenkov telescopes, like magic in La Palma, they have just the right requirements. They are very large, so they collect a lot of light. You need a lot of light to see these fluctuations. They have mirror parabolic shapes, so the time response is fast, less than 1 nanosecond time response. They are sensitive to optical wavelengths because the Cherenkov light that we detect is blue or near UV. The photodetectors are fast, so you also have fast time response coming from the photodetectors. And actually the whole electronics is very fast. So we can work with this 1 nanosecond is easy for these Cherenkov telescopes. You don't need to make you only need to make very few changes. We are essentially, what we are doing in MAGIC, for instance, is we place some filters in front of the photodetectors. We use the same photodetectors that are already there in the telescopes. We bring the signal same as we do for all the other pixels to a digitizer in a counting house near the telescopes. We digitize, this is new, we digitize the light, 500 mega samples, so 2 nanosecond beams, okay? And we correlate using a GPU. This is all possible now because we have all these GPUs and digitizers that are very fast and actually very cheap, okay? So this is from the last years. We can do it easily. And we see immediately when we switch on the whole thing, we could see nice correlations for stars actually in real time with the GPU, okay? So we see these nice correlations. We started back in 2019 with some first results in, here there was a paper here. We started in 2019. And with a more professional interferometer, what we are doing has been just published. This is a study of the performance, actually, of the interferometer, of the MAGIC interferometer with the two MAGIC telescopes, and the measurement of a few stars. So what we see is this nice correlation versus baseline that I talk about. So we see the correlation dropping slowly with the projected. This is the baseline. This is 60 meters, 100 meters. Okay. So you see this nice drop with the right shape. And from this, you can fit it to the expected function, and you get an estimate for the diameter of this specific star. It's a very bright star, Epsilon Canis Majoris. And you get an estimate that is like 0.76 milliarcseconds. So we are talking about this kind of diameters with an error of 0.02 milliarcseconds. So 700 something microarcseconds plus minus 20 microarcseconds. Okay, these are very, the errors are very small, are in the order of tens of microarcseconds. Okay, remember that EHT works with this kind of tens of microarcseconds. So we are already there. Of course, we are in optical wavelengths. That means we have better resolutions than radio wavelengths. Okay. Okay, so this is an example for a bright star. we have been measuring several stars. So we started by looking at stars with previous measurements in phase interferometers or amplitude or intensity interferometers. We remeasured the diameter, and this is what is plotted on this axis. And this was the previous measurement, and this is our measurement. So we plot them to see if we are consistent with previous measurement. Okay, this is a consistency check. And for these stars, we are consistent. There's a guy here that is a bit far, but statistically we are consistent. We are actually also checking the signal to noise, the sensitivity of the experiment compared to our expectations, and we are also consistent once you consider that you have some drop in sensitivity due to simply atmospheric absorption of technical problems and so on. So we are consistent. Okay, so performance is okay. So we move to measured diameters of stars that had not been measured before. So these are new measurements of diameters. And we compare to models here. So this is our measurement, and this is the theorized diameter, the model diameter, for again, many more stars. So these are new measurements. And we are comparing with the models. And what you can see here is there's a nice correlation with the models. So what the models are predicting is in general okay. There are exceptions, like this guy here. And these exceptions are actually the interesting ones, right? So that's by, well, it can go, the distance, the spectral type, and then the model can be more or less refined, right? Okay. Yeah, okay, so there are a few disagreements. In general, the models are okay. We are starting with this. We are actually starting a small collaboration with a group of massive stars here in-house to see if the models are in general okay. Okay, it's the group of Artemio and Sergio. Okay. But this is not enough. We want to bring more telescopes into the game. Okay. So as you can see here, the kind of stars that we are looking at are actually relatively bright. So we would like to add more telescopes so that we are more sensitive. So that the baselines, this is the distance between the two MAGIC telescopes is 86 meters. So by adding more telescopes that are farther away, we increase the baseline, and that means we can go to smaller stars. Okay. So we plan to go to weaker and smaller stars. So these are the MAGIC 70-meter telescopes. And as you know, what is going on at Roque is this construction of Cherenkov telescope array telescopes. The LSTs, large-sized telescopes, are 23-meter diameter. Okay, LST1 has been there for a few years, but we are right now, as we speak, building LST4, 3, and 2, all at the same time. They have 23 meters, so they collect much more light. They are more sensitive. And the installation is expected to be completed in 2025. So it's a matter of a couple of years that we start to get data with all these telescopes. We have large expectations. This is the error that you get in the diameter. This is 10% error in the diameter as a function of magnitude of the star in 100 in 2 hours. So in 2 hours with MAGIC, we can go to a 3.5 magnitude star, and we get an error in the diameter measurement of 10%. If you start to use also together with MAGIC the LST1 telescope, you can go to weaker stars, 4.8 magnitude. And if you go to the 4 MAGIC plus the 4 LSTs, you can go down to almost 6 magnitude. Okay. These are very bright stars, right? 6 magnitude is a very bright star, but still you see that there's a huge increase of sensitivity down to magnitude 6 when adding the 6 telescopes. Actually, my colleague Tarek Hassan from CIMAT has got a ERC starting grant to design and test this interferometer. Okay, so the money is there to build the interferometer. just a reference number. Yeah, we can go for whatever. I mean, some of these measurements we made are tens of hours. Yes. But 2 hours may be something you can do in one night, for instance. So it's a useful reference. Sorry? Yes. We are actually taking a lot of moon time that is not very useful in gamma rays, but with these stars that are so bright, we can take moon time. Okay, so we can even take data in full moon, for instance. That's what we are doing right now. Okay. Adding more telescopes is not only good because you are more sensitive. It's also good because you have a better spatial reconstruction. So when you look with two telescopes at one star, you are only looking at the star in one specific orientation in the sky, along some direction in the sky. And this is shown in this UV plane. Okay, UV plane is the projection of the sky into your into the ground. Okay, so when you observe along the night with magic, say you're looking at the you're hardly changing in the UV plane. So you're looking at the star always in some specific direction. When you start to use many telescopes, you start to look with the different pairs of telescopes, you start to cover the UV plane. So you start to look at the stars, say, in many different directions. You start to do some kind of imaging of the star. This is, for instance, the coverage with all the combinations of magic and the 4 LSTs. Okay. For instance, for a star that is distorted, that is not perfectly spherical, it's not perfectly symmetric, what you expect to see in the ground is a distribution of visibility that is also distorted. If you look only in this specific direction, you will never see the distortion. When you have many telescopes, you can see the distortion of the star because you're looking in many, many directions. Okay. So this is also very important for us. So implementing all this in the LSTs, I'm not going into details, but it was very easy. So we could modify part easily some electronics in the camera, or in the existing camera of LST1, the first telescope. We could add the filters, reusing some mechanics. So it was relatively easy to implement. It's already implemented in LST1, in the first Cherenkov telescope, and will be available in the next LSTs from day one of the operation. So hopefully in 2 years, everything will be ready. So for LST1, we actually put it to work this year, 3 months ago, 4 months, 5 months ago, in January. So far we have taken only 30 hours of common observations of bright stars, but from the first night we could already see some very nice correlations in the now 3 pairs of telescopes. So the 2 magic telescopes plus 1 LST, we have 3 pairs. And here, for instance, in a star, you see these nice correlations, 3 correlations coming from the 3 pairs. We've been looking already at weaker and smaller stars, less than 0.4 milliarcseconds, okay? Which will be interesting, as you will see, for fast rotators. So this is also what you can see for a couple of stars. Now, not only with the magic 1, magic 2 correlations in orange, but also in blue and green with magic 2 LST1 correlations and magic 1 LST1 correlations. So we are doing this already with the 3 telescopes. Okay, so what kind of science are we planning to do in the next few years? And we're already doing. I will focus on 3 examples, essentially. The first one is simply to go on measuring stellar diameters. This is done already. I mean, there's already many measurements coming from phase interferometry of many stars. So you may argue why we need a new instrument for this. And the reason is that with intensity interferometers, we can explore this area here, where we will go to weaker and smaller stars down here with diameters of only 100 or 200 microarcseconds. Okay. And even maybe more interesting is that we can go, as I said, most of the phase interferometers operate in the infrared. Okay, here we can go to blue or near UV. It's straightforward for us. And that means that we're especially sensitive to O and B type stars, massive stars. So this is where we are focusing right now, early type stars. And what is also very interesting is that many of these stars are fast rotators. Okay, fast stars are not spherical cows. They have actually a shape. This is something that is not very much appreciated because we are typically not able to measure these shapes. For a few stars, the shape has been measured with phase interferometers. Okay, and we are talking about very large stars like Regulus, Altair, very bright stars. Measuring the shape of the star has implications because there's actually a brightness distribution in the star caused by the distortion, by the rotation speed, which has there's an impact on convection due to the rotation. There are connections with asteroseismology because this will go into the oscillation modes, and it also helps to understand wind injection. Rotation is probably adding to the wind, to the injection of the wind. In many of these stars, there's a very strong wind. Right? And it's not that there are many measurements, there are very few measurements. What you see here are not just examples, they are essentially all the measurements that have been done. There's not more than 10 stars which has been measured, whose shape has been measured, right? So there's a total lack of measurements of the shape of stars. What I like to show you, and this is very preliminary, and I think it's the first time that has been shown in public, is some first results with MAGIC. With MAGIC, we have been measuring one of these fast rotators, one that has not been measured before, gamma CAS. And this is what we can see. This is in polar coordinates, stellar radius. This is 0.2 milliarcseconds, this circle here. And this is our measurements, right? So what we see is a dependence with azimuth in the sky. Okay, so we see the distortion of the star. Okay, there's a significant distortion. We see a change in the diameter of the star by almost at 20%. Okay. This actually has also been a matter of master work here at IAC by Fernando Barnes, where you can see also numbers. I mean, you can see the change in the equatorial diameter between the equatorial diameter and the polar diameter is as much as 20% from 600 microarcseconds to 500 microarcseconds. Okay. So you see this change. You see also the orientation of the star in the sky, right? I mean, you see that the rotation axis goes in this direction. Okay, so it's possible. It has been done already with MAGIC, even with this very small coverage in the UV plane. Okay, now by having LST1 in the picture, we can do it even faster, do it even better. So how many fast rotators are within reach? So here, this is a plot by Alejo Cifuentes from CIMAT. It's been shown these days at the SPIE conference. And what I show here is the deformation of the star, what is called oblateness of the star. This would be a very symmetric star, a perfect sphere. And this would be a very distorted star, very fast rotator, as a function of magnitude. So this is based on a catalog of existing stars where we know the rotation speed. So we can predict what is the oblateness, the distortion of this of the star. And this is the magnitude, right, for different angular diameters. So as you can see, this is magnitude 6. So there are many stars that are within reach. Most of them are essentially within reach of MAGIC plus the 4 LSTs. This is just one example. You take this star, Zeta Piscis. We have made a simulation. This was by Tarek Hassan. Okay. where you see that there's a very nice coverage in the UV plane. And what he did was to try to reconstruct what we would expect with MAGIC and the 4 LSTs. He produced the visibility curve, he fitted it, he got an estimate for the diameter of the star, the orientation of the star, and the oblateness of the star, so the deformation of the star. And these are the errors that he's getting. So for the diameter, we can measure the diameter with 2% error, okay, for this specific star. We can measure the orientation with an error of only 5 degrees, okay? And the oblateness with an error of 5%, which is amazingly small, okay? So we can do this for this star, and that means for many of these stars, we can get this kind of errors with the 6 telescopes. Of course, there's something, you go to targets that are even more exotic, say, like interacting binaries, you should also be able to see something like this, right? If there's a distortion of the star, for instance, because there are 2 stars that are coming close to each other, like the heartbeat stars. Like this is a rendering for Iota Orionis. If there's a distortion of the star, we expect also to see this for bright targets. We still don't know if there's one within reach, but in principle, that would be the idea. That's also the idea. It's also the idea to do it for contact binaries, where you actually have 2 stars that are distorted. What you see is actually a light distribution that if the target is bright enough, maybe we are able to see, okay? Okay, there's something that is also very interesting for us, which is novae, where there's actually a connection even with gamma rays. We are doing the same. We are also serving novas now with Cherenkov telescopes because we detected one of them at Astrofísica a few years back. What we are interested to see is when the nova happens, the photosphere, so-called photosphere, will expand very quickly, right? And this is what we expect to see. Has been done only once with a phase interferometer. Chara, one of the ones that I showed you before, what they measured was the angular diameter. This is in milliarcseconds versus time, and you see really the expansion of the photosphere of the nova, okay? So you see the ejecta growing, okay, in space as a function of time, and you even see a change in the speed in time. This was published back in 2014, sorry, for this specific nova Delphini, okay? And the expansion speed was 0.14 milliarcseconds per day, okay? So they could cover the expansion for almost 1 month. Now, when you look at novae, but after many years, this is what is shown here. This is, for instance, for this nova, 13 years after the eruption. When you see sometimes it looks symmetric, but sometimes it doesn't look symmetric at all. So sometimes you see structures like rings. Sometimes you see a totally asymmetric eruption where the ejection is very much only in one direction. Okay. Even in Astrofísica, the one we observed, there's evidence for bipolar ejection. Okay. But these are many years after the eruption. So the ejecta has expanded to huge angular sizes like 2 arcseconds. Okay, so we would like to study this in the first days after the eruption and to see there's already asymmetry in the eruption in the first days after the eruption. There's actually a star, I guess you all know from the news, it's been in the news everywhere. This T Corona Borealis that is probably about to erupt. We have very big hope. It has even been in the sports media, so you can imagine the degree of attention that is getting. And we have been evaluating the prospects for studying the expansion speed of this star, this nova, with our interferometer. This is with MAGIC, only with MAGIC, 10-minute measurements, so 10-minute snapshots. 1 year after 1 hour after the eruption, 2 hours, 3 hours, 4 hours. This is the kind of errors that we are getting. So rather small errors. if the shock velocity, for instance, is 3,000 kilometers per second, we would perfectly see the expansion of the photosphere for a few hours after the eruption. That's the problem with this nova, that it expands very fast. Okay, with the distance and the expansion speed that are expected, we would need to look at the nova in the first hours after the eruption. It will be very critical. Now, if we manage to have LST1, and that's something we are trying very hard to do, MAGIC plus LST1, you see the errors that we are getting in 10-minute observations. They are tiny. So we could measure the speed with a very, very high precision. Even with 2 or 3 measurements, we will be able to. In the future, with the 4 LSTs, it would be incredible. I mean, you cannot see the errors in these kind of expansions. But with 4 LSTs, what is, or even with LST1, what is fantastic is you have also this nice coverage in the UV plane. So it's not only that you see the expansion in one direction, so you have to assume asymmetry, but it's also that you can see the expansion in many directions, okay? You loosen sensitivity, but with these errors, you do this in several directions with all the several pairs telescopes, you can indeed measure the expansion in several directions. This is actually the prospect for a weaker nova, because not every day you get T Corona Borealis. This is actually a once in a lifetime event, but a weaker nova like a 5.5 magnitude nova 3 kiloparsecs away, and assuming different expansion speeds, we would also be able to see with MAGIC plus 4 LSTs nicely, we could nicely measure the expansion speed. And if the nova expands much more slowly, this is hours. So as you can see in blue here, this is a shock velocity of 200 kilometers per second. It would take days to expand, so we could measure it much more nicely over several days. Okay. Okay, so I'm already reaching my conclusions. I hope I'm perfectly on time. As follows, I mean, as I try to show, contrary to phase interferometry, intensity interferometry is a new technique. You can go to very large baselines, and you can observe a short wavelengths. Okay, deep in the visible, down to blue wavelengths. Okay, so MAGIC has been doing this, has been using this technique for a few years already, and we have already measured stars in this angular range, less than 1 milliarsecond. The LSTs are under construction. Actually, I didn't add it here, but LST1 is already taking data with MAGIC. Okay, but the next LSTs will come very soon. We will go to even shorter angular resolutions, less than 100 microarcseconds. These kind of observations are short wavelengths, are good for massive stars, as I showed. And we hope to characterize the parameters of fast rotating stars down to 6 magnitude. So there are a lot of targets that we could actually look at. And we also expect to see the evolving photosphere, the expanding photosphere of the brightest nova, measure the speed and the asymmetry. Okay, so thank you.
Okay, hello, yes, so now we have time for questions.
It's fantastic work, really, very, very exciting. A question, could you comment on the effect that you expect from seeing? Because I expect that, I mean, the fact that you have this turbulent medium will decorrelate your signals to different sources. And the second point is about whether there is any hope of detecting quasars, this technique.
Okay, so the first question is easier to answer than. There's no effect of seeing. Really, there's the. I mean, to begin with, the kind of resolutions, angular resolutions that I mean, okay. So the ability, the fact that the star gets smaller or bigger due to seeing is totally relevant for us, and the effect on time, yeah, the effect on time is also relevant because the kind of correlations that we measured are in the nanosecond time scale. Okay, so the effect of seeing may produce changes in one telescope respect to the other one, but they are in much longer scales. Okay, so we are talking about so different time scales that there's no effect at all. Mhm.
My point, or the reason what I'm asking is not because of the time scale variation seen, but the fact that since the two telescopes are so separated in space, they see a different atmosphere. And the time delay produced by the atmosphere is larger. It's nanoseconds that I think.
So it has been studied. This has been studied. The effect is in the order of 30 picoseconds, something like that. This is the number you want to keep in mind. It depends on the quality of the sky. Okay, so it ranges. Sometimes it can be up to 30 picoseconds, and sometimes it can be even better than that, 10 picoseconds or something like that. Has been studied. Yes. Okay, so the quasar. The quasars. The problem with quasars is they are very weak. Okay, so it's impossible to find a quasar that. You find me a quasar that is brighter than 6 magnitude, I can do it. Okay. There's also the matter that they are very small. Okay, so you would have to go to even longer baselines. This would not be a problem, but the problem is really brightness. Okay, so there's an effort in this respect. So there are already people trying to achieve higher sensitivities, and okay, I don't want to go very much in detail about this, but there's sensitivity in this technique. This is sensitivity. So it's proportional to several factors. One is mirror area. That's why I'm telling you, you have to collect more light, so you go to larger telescopes. Okay, so you typically need large telescopes, tens of meters. There are not so many on planet Earth with tens of meter diameter. Well, efficiency of the photodetectors, number of telescopes. So you need many telescopes typically. But it also goes with two more factors. One is time resolution. So you go to photodetectors that are much faster. We are talking now, our photodetectors are 1 nanosecond. They have 1 nanosecond time resolutions. You go to picosecond time resolutions, which is possible. Okay, you could improve the sensitivity with the square root. Okay, you could also play a trick, which is that we are working with a narrow filter, actually, of, well, it's not so narrow, but it's like 20 nanometers. Okay, there's a trick here. In intensity interferometry, when you go from 20 nanometers to 2 nanometers, for instance, so you make the passband of the filter 10 times smaller, you get exactly the same signal, to noise, because you get fewer photons, but they are better correlated. Okay, so it's a very nice trick. You can get the same signal with a smaller passband. And that means you go and add another channel taking data on the same star at the same time, simultaneously at another passband of 1 nanometer, or okay, by adding many channels, you could add the signal from all the channels. So by having many spectral channels at the same time, with indefinitely small, actually, passband, you could add much more signal. So say you consider n spectral channels, it goes with the square root. So you would increase the sensitivity by adding many spectral channels. Okay, but we can use these two facts, these improvements due to time resolution and number of spectral channels, and that's something that is attempted now by some Swiss colleagues who are trying to have at the same time many spectral channels, up to 1,000, and very narrow ones. Okay, very fast time resolutions, down to something like 30 picoseconds, which is the limit of the atmosphere, as I said before. Okay, so by having these, they expect to achieve magnitudes down to something like 11 or something like that. So what they are targeting really is the accretion disk of AGNs. Yes. Mm. Sorry? Yeah. They are targeting the very brightest ones. So they cannot, it's not that they will reach the whole population. Yes. Mhm.
Okay.
Yeah, I have a very naive question. So, can you combine the Cherenkov with, say, other telescopes in the optical to stare any? It's completely crazy.
No, it's not crazy at all. I mean, that's I have some other backup slides about that. But for instance, I mean, we've been thinking on this, obviously, and there's at least one telescope that has more or less the same size as our telescopes, the GTC, 10 meters. Okay, remember that magic is already 17 meters. Okay, so GTC is at a baseline of order of 500 meters. And if you consider the William Herschel, for instance, is 1 kilometer away, so you would have fantastic baselines even at Roque. The problem is they are relatively small size, so you lose light. So you would need to compensate somehow by having faster time resolution, as I said before. Or I mean, you would need to implement, say, new photodetectors both in GTC and the MAGIC and the LSTs. Okay. Or you could have some kind of mixed array where you have worse resolution here, better resolution here, something like that. Something we have in mind. We are thinking on that. We may eventually do it. Yeah.
My question is related to the time correlation. Because if you need to be sure, you say that you're recording on a tape that at what time you're receiving the photos. And I guess that you need to be sure that with enough accuracy, the two tapes are recording, that they are measuring the same relative time. So what is the precision that currently that you can, because that it will be uncertain, no? You are using some clock somewhere, and you have to be super precise, and you have to provide with the signal to the telescope to say this is the right time right now. So this is a limitation at the moment.
It's not a limitation for one simple reason. I'm trying to get to the right slide. Is that we are bringing the signal, we are bringing the actual photon pulses from the two telescopes with very high time accuracy. We are bringing them to a common place where we digitize at the same time using a card, essentially the same card or card that are very accurately synchronized. Okay, so when we say that we sample with 500 megasamples a second, we are sampling essentially with the same clock. Okay, so we're
That they call that
yes. Yeah, but this is, I mean, 1 nanosecond is nothing for us, as people in Cherenkov telescopes. We require that anyway. So everything is designed for these precisions. 1 nanosecond is 30 centimeters. This is a macroscopic distance compared to, I mean, we are used to these precisions. We can achieve that. Yeah, I mean, I mean, your question is very relevant when you try to do it for telescopes all around Roque, for instance. You will probably have to digitize locally and synchronize using some common clock. So here we are using technologies that we are also testing in CTA in general, like White Rabbit, where it's already 100 picoseconds is already achieved. But we expect to go down to 10 picoseconds. Okay. So for those, it's really tricky, and we are at the limit of the technology. But for 1 nanosecond, it's nothing. Yeah.
Yeah, I wanted to ask, I see that you are picking up, well, the limitation the universe now is constrained to stars, individual stars. So I was wondering whether you get in more compact regions, but still a cluster. So you could measure stars in a cluster. You could measure sizes. So you can even somehow constrain the IMF because you have different sizes. So what will be the limitation if you look at a cluster of stars in our Milky Way? You can go to this distance. You are some stars, a kiloparsecs.
Okay, the problem is the actual the problem is our pixels. They have a field of view. Each individual photodetector has a field of view that is very nice for Cherenkov astronomy, but is total shit for this kind of astronomy because it's 6 arc-minutes. So you integrate the light in these 6 arc-minutes. So you have 1,000 stars, they all go in. And then what you are looking at are correlations of all the stars at the same time. Okay, so we had to pick stars that are isolated. So that are more than 6 arc-minutes away from each other. Yeah.
So before the very beginning of the presentation, you mentioned that parabolic their Cherenkov telescope such as so what's the effect?
Okay, so you degrade timing. Yes. In the MSTs they are not parabolic. MSTs are the other type of CTA telescopes, 12 meter, that will also be installed at Roque in the future. They are not parabolic. They have a funny shape. Still, you get some time resolution. It's not that you are totally degraded. So working at 1-2 nanoseconds time beams is not so bad. It could be very bad if you try to go to 100 picosecond time resolutions. Then you're totally off. For GTC, it's not a problem. The rest of the optical telescopes, I mean, they have secondary optics, and that compensates for that. So at the end, you get this kind of time resolution. That's not a problem for optical telescopes.
So one more question, and then we will go for the coffee.
Well, actually, I have two. One is you were talking about massive stars, which are blue, but there are also a couple of bright red giants. Have you tried them? Which have been done with Shara, for example. Have you done red giants, and how do the results agree? Do you see differences? And the second question: what is the potential of launching such technique into space? What would it take to have a space mission?
Mm-hmm. Okay, so yeah, red stars. I mean, consider Betelgeuse. I mean, you see that the baselines that were involved were a few meters. So, and the baselines we are talking about are hundreds of meters. So they are simply too large for us. Okay. We have actually we have actually doing something very fancy, which is to do interferometry even within one telescope. In one mirror, we split the light. One part of the mirror goes into one photodetector, the other part goes into another photodetector. We make correlations of the two parts of the mirror. And with that, we managed to measure the diameter of Sirius, which is something like 6 milliarcseconds, 3 or 6, something like that, a few milliarcseconds. But Betelgeuse, for instance, is 50 milliarcseconds, so it's impossible to reach. Other red giants, maybe something like a few milliarcseconds. Still, they're pretty large for us. Okay, and we have some limitation. When you split the light, you lose light collection, so you lose sensitivity, and so on. Okay, so in general, red giants are too large for their brightness. Say for the same brightness for the same magnitude in B, they are much larger. Okay.
So
No, I don't think so. We can try now with the LST1. We have better sensitivity, and maybe we can measure a few of them. But I mean, we are convinced of our performance because we have measured already many of them. So we are not. And then you talk about space. Now the problem with space is that when you want to bring a 70-meter telescope to space, yeah, you will have problems. But you need to collect a lot of light for this kind of interferometry. But I mean, I attended the last SPIE 2 years ago, and there was already somebody talking about why not doing intensity interferometry in space with smaller telescopes, better angular time resolution, and so on and so forth. So it's a bit of speculation.
But so you cannot without.
Well, scintillation is not an issue, as we will discuss later in the coffee. But scintillation, same as any atmospheric effect, is not an issue. And the exposure time is fine, you can compensate, but if it takes years, at the end, it's totally useless. And there are ideas also to bring it to the moon. Yeah. You won't believe it, but some of those people are considering that.
Okay, I think it's time to stop. Thanks Juan once again. And remember that now we will have the scientific coffee where you can keep on discussing with Juan.